Okay, hi Zach. Welcome to lesson number 60. This starts on page 242 in your book. This one goes over geometric solids and it also goes over prisms and cylinders. So I think it's going to be actually kind of fun. It's kind of nice to have one like this before we get into the really difficult, challenging math that's coming up later in this week. So enjoy this one while we're doing it, okay? Here, these kids are learning about perimeter, and their teacher is obviously teaching them to add the length of A, B, C, and D there. And one of the kids is saying, or you could just walk around the edge and let your fitness tracker tell you the distance. yeah, that would actually work too. When you can do that, sometimes you can't do that. So there you go. All right, so let's jump into geometric solids, okay? So a geometric solid is going to be a geometric figure that has 3 dimensions. And we're going to go over some of them. I'll show you some of them that they point out in the book. There's a triangular prism. Okay, so the first one that's shown in your book on page 242 is this triangular prism right here. And this side right here is actually the base. There's another base on the other side. So in this example, the prism is sort of laying on its side. But on the example in your book, it's sort of, upright the other way. It would be going upright that way. And it would be standing on the base. So it has 2 bases. And then the faces that it has are 5 faces total. These are edges. So these are called lateral edges because if it were standing up, that would be on the side. And then vertices is how many points does it have, like that. So that's a triangular prism, and it happens to be a right triangular prism because when you do stand it up, it's going to be standing straight up at a right angle. Okay, so that makes it a prism, a right triangular prism. Okay. All right, so the next one it goes over is a right circular cylinder. Where is that one on here? It's this one. This is a right circular cylinder. And so the base on the top and the bottom is a perfect circle. Again, it's a right angle, so it's a right circular cylinder. The bases are 2. Here's a base, here's a base. It doesn't have any lateral edges because there's no areas where it sort of comes to a sharp edge there. And it's not said to have any vertices either, or really faces. This is going to be called something different. It's going to be called the lateral surface area, and we're going to learn about that coming up. Then there's the regular square pyramid, and that one's here. This is a square pyramid, and the reason it's called a square pyramid is because the base of it is a square, is standing on a square right there. So the book says these are sort of informal definitions. You can look at these and sort of identify what they are, but to define them mathematically is a little bit hard. I kind of don't love that. This is the first time I haven't loved your book because a couple times this week I've noticed it says something like, well, this explanation is beyond the scope of this book, and so I'm just going to tell you. And I don't know, I don't totally like that. Like, just tell me the definition and I'll see if it's too hard for me or not. Like, why does the book decide? But anyway, this is a regular square pyramid. They call this one a rectangular pyramid, so I guess this is not a perfect square if it's a rectangular pyramid, but the concept is the same. If this were a square, it would be a regular square pyramid. Then you have a circular cone. That's this one. Okay, so this is a circular cone, which means it's a circle at the bottom, but if you draw an axis right to that point in the middle, that part is going to be a perpendicular right angle, a straight line there. Okay, so it just has only one base, only one vertices right there, and no faces or edges because there's no edges here. The edges have to be on that lateral side, and so does the faces if there is a face. So this is just also called lateral surface area. Okay, and then the sphere is the last one that they show you, and I don't know if I have a picture of a sphere. No, I don't, but you know what a sphere looks like. It would be a perfect circle in the middle. The radius would be the same at that center point to any edge of the sphere. Okay, so now what they want us to focus on in this lesson is the prisms and the cylinders, okay? So not all of these are prisms and cylinders. You can see that this is called a cone. That's something different. This is called a prism. This is a cylinder. This one's a pyramid, so we're not going to talk about that today, but this one is a prism. And this one is a prism. This one is a prism. And this one is a prism. So what makes it a prism? And basically, prism is this. It has two faces. And the faces are the bases. The bases are identical. In fact, I don't like how it calls it face because that is confusing to me. A face seems to me that it would be on the side. You don't stand on your face. You stand on your base. Whoops. Okay, so you stand on your base. And they're identical and they are parallel. Meaning like if you've got a piece of paper that this is standing on, okay, this is a piece of paper, and then you can perfectly balance a piece of paper on the top. It would have to be like a cardboard paper or something like that. Then those pieces of paper are parallel to each other. They're perfectly parallel, okay? So that's what makes a prism. The bases are identical. This has to be exactly the same as this, and they have to be parallel. The other faces, these are called the lateral faces. So the lateral face is this face. This makes more sense to me to call that a face because it's sort of what's looking out at you. And you can see that there's three of them. There's one kind of behind there that goes there. And then there's one kind of sideways looking up on this one, that one. So there's three of those lateral faces. And then you've got a lateral edge, and that's where the faces meet. So there's a lateral edge here, there's a lateral edge here, and there's a lateral edge here. I want you to notice that this is very different from the altitude or the height. Because this one is an oblique prism, the altitude or the height is different from the length of this lateral edge. So obviously this is going to be longer. That lateral edge is going to be longer. The way you get the height is if you perfectly balance that piece of paper on top of the prism and you perfectly balance a piece of paper that the prism is standing on, the height is that difference between those pieces of paper right there. Okay? So the height is always going to be perpendicular. Okay, perpendicular. So the height is at a right angle, even if the prism is oblique. Okay. Okay, so now let's look at this one. This is a special type of prism, and it's called a right prism. And a right prism means that these lateral edges right here, all of them are perfectly at right angles to the base. I think you can see that. That is a right angle, and they're all going to be a right angle to the base. Okay, and so when that happens, it's called a right prism because there's all those right angles in there. Notice that in the right prism, this lateral edge and this lateral edge is actually the same as the altitude or the height, and that's different from oblique. Okay, so you can use this as the altitude or the height only if it's a right prism. Okay, this is the base, and there's another base down here. And then just to review, the lateral face is one of these faces, and there's two in the back right there. And then the lateral edge are where those lateral faces meet. So right there, and there's a bunch of them. Okay, so that's the right prism. Okay, now prisms are classified and named according to the shape of their base. So they're going to get a name. It's not just a right prism. Right prism is a whole group of geometric three-dimensional shapes, but they're named according to the shape of their base. So prisms are classified according to the shapes of their bases. So these are some of the examples that they show us. We went over the right triangular prism. So this is a prism, but it's sort of laying on its side. This is the base because there's the triangle. Okay, so it has those two bases, but it's called a triangular prism because the lateral edge is at right angles to the base, so that's a right angle, and also because the base of it is a triangle. Okay, then there's the right rectangular prism. A right rectangular prism is this one. So this is kind of like, I don't know, it looks like a brick, right? So the base is, well, I guess you could say that this is the base because it's a rectangle. And then there's two of those bases. And then the lateral edge is at right angles to the base. So that's true. And the base is what gives it its name. It's a right rectangular prism. Okay. Then they show you a right trapezoidal prism, which I don't have an example of here. There's just not one. I guess this one is kind of one, but this is also the pentagonal prism because the base of it is a pentagon. Okay, so this base, whoops, it won't let me highlight. This base and this base on the bottom is a pentagon, so that's how it gets its name. It's a pentagonal prism. It's also a right pentagonal prism because the lateral edges are at right angles to the base. Okay, now, alrighty, I think you get that. What about a cylinder? Then it says to go over a cylinder. A cylinder is like a prism, except the bases are closed curves. So this is not sort of a polygon, it's just a circle. It's a circular shape. And you can have a right cylinder, You can have a right cylinder, and that means that the face of it, no, they don't measure it from the face. What they do is they measure it from the axis. So let me show you the axis. Okay, so if you put a dot right in the center of the circle on top and right in the center of the circle on the bottom, okay? And then you draw a line down the center, and that's not a very good line, but that's the axis. It's the very center of the top base, the very center of the bottom base. And if this is a right angle to the base, then it's called a right cylinder, okay? And this would also be the altitude or the height of it. I'll call it the height. What else? This is the base. Oh, this is called, like the outside surface of it, if it were like a soup can, the outside surface is called the lateral surface. Okay. And this is called the axis. What else? The other base is here. So this is a right cylinder. Okay. The axis is perpendicular to the base. We talked about that. And the axis is also the altitude or the height. We talked about that. Okay. Now, this is also a cylinder. This is just an oblique cylinder, but it still is called a cylinder because the top is a closed circle, the bottom is a closed circle. If you put the pieces of paper that they're standing on and that you balance on, they would be parallel to each other. But in this situation, the axis is not at right angles to the base. That is not a right angle. That is something less than a right angle, okay? That would be an acute angle. And so because of that, the axis, which is here where you connect the center dots of the top and bottom circle, is not the same as the altitude. It's going to be longer, right? Because if you make a triangle like that, the axis is the hypotenuse. It's going to be longer. But the altitude is if you take that piece of paper on top, take the piece of paper on the bottom, connect them by a right angle, that's going to be the height. Okay? So this is a cylinder, is just not a right cylinder because there is no right angle there. It's an acute angle. Okay. All right, let's move on from that. So cylinders are classified and named according to the shapes of their bases. You can have a right circular cylinder, and I think that's what this one is. If the base is a perfect circle, then that's what this one is. If it's, something like that, then it's not a circular cylinder, it's just a different cylinder. Okay. So now when they give us problems at the end of this lesson, we're going to assume that they are right circular cylinders, because that's what we're going to be dealing with, okay? So right circular cylinder has a circle at the top, a circle at the bottom. The axis is the height. And this distance, since it's a circle, you can get a radius right there. And this is a right angle. Those are the important points. Now, if it is true that you have a right circular cylinder, then the volume can be easily calculated. And I look at this cylinder and I see a cup of refreshing cold water. Ah. Have you ever experienced that? Like on a really hot day and you just drink a cup of refreshing cold water and you say, ah, that tastes delicious. Well, the volume that you're drinking can be easily calculated in 3 easy steps. Just kidding about the 3 easy steps. But this is the volume of prisms and cylinders. And this is in a thought cloud. This is something that you're definitely going to have to remember and memorize. So take a little bit of time right now and just memorize this equation. The volume of prisms and cylinders is equal to the area of the base times the height of the cylinder. The area of the base times the height. You definitely need to know this. And remember, the area is going to be in something like something squared, right? Maybe it's centimeters squared or it's something meters squared. It could be feet squared, could be inches squared, millimeters, anything. But it's going to be something squared. And then the height is going to be in just a unit of length. So when you end up getting the volume, it's going to be millimeters cubed, right? Something cubed, meters cubed, maybe feet cubed, something cubed. And that's a volume, and so that makes sense. So let's jump into an example and just see how it works in action, right? Example 60.1, it says, the area of a base of a right pentagonal prism is 28 centimeters squared. So that's super nice because they just gave us the area. They didn't expect us to calculate it. So they're saying the area of the base of this pentagon thing is 28 centimeters squared. So I'm going to write 28 centimeters squared here. Then it says that the lateral edge, so this is one of the lateral edges right there. The distance there is 10 centimeters. Find the volume. Okay, this is easy peasy. They gave us everything we need to know to figure this out easily, right? Now, the volume is like a cup of refreshing cold water. Ah. The volume is equal to the area of the base, which is 28 centimeters squared. Don't forget your units, times the height, which is 10 centimeters. So what am I going to get? I'm going to get 28 times 10, 280 centimeters cubed. And this is my final answer. I'm sticking to it. And luckily, that's the same answer that they got in the book. So easy peasy, right? You can calculate the volume of prisms or cylinders now. Now you can imagine when you look at this problem, what kind of problems they're going to be giving you. You're probably going to have to calculate the area by yourself on some point, right? You're probably going to have to figure out the height in some way, right? You're probably going to have to realize that the height is different from an oblique height, right? So you can already anticipate what kind of questions you're going to be asked, so that way you do not get tricked, because don't let them trick you on these easy things. I want credit for the stuff you know, right? All right, now we're going to talk about the surface area of prisms and cylinders. So let's say we don't want to know the volume. Volume is how much water would fill that container. But the surface area is like, if I need to put a label around the container, then what's the area of that label going to be? So the lateral surface area, if we get out our dictionary and look it up, the lateral surface area is the area of all the external surfaces except the bases. So don't let that trick you. It's like a soup can, right? It's like a soup can. You don't need a label on the top and the bottom, right? You just need a label around the lateral surface areas. So that's what the lateral surface area is. You're just going to be calculating the area of those side surfaces, not the top and the bottom. Easy peasy. How do we compute the lateral surface area? Hey, it's as easy as childbirth. You're gonna, it's a little more complicated than volume, but you're gonna get it right away. Okay, you're gonna get this. It's gonna be great. So, lateral surface area of right prisms and right cylinders. Here's the equation. It's in a thought cloud. You have to memorize this. The lateral surface area is the perimeter of the base times the height. What's the perimeter? Just like if you take your Fitbit and you walk all around the edge and it gives you a number, that's the length of this. It's the length of the circle, or the length around a pentagon, or the length around a rectangle. Whatever this shape is, if you walk around it with your Fitbit and it tells you a distance, that's the perimeter. What about the height? The height is this height, h, as long as it's a right angle there. Make sure that it's not oblique. If it's oblique, then you have to find the perpendicular distance between the top and the bottom. So LSA is the perimeter of the base times the height. And that's how you figure out lateral surface area of right prisms and right cylinders. So the height, because these are right, the height is always going to be this perpendicular distance. Okay, let's do it. Oh, I want to show you how that equation actually makes sense. Because in this situation, when we're calculating the lateral surface area, we're calculating an area. And if you take a soup can and stretch out the label, it's the area of a rectangle that you're figuring out. And you already know, you have memorized the equation for an area of a rectangle. It's the base times the height. And the base is just that perimeter around the base, right? It's this distance, it's that length. And that is the base times the height. So it totally makes sense that it would be the lateral surface area is the perimeter of the base times the height, because you're basically calculating the area of a rectangle if you were able to stretch it out. Okay? So let's jump into an example. And don't worry, the force will be with you as we do this. It's going to be great, okay? Example 60.2. Find the lateral surface area of this right prism. It's important that they tell you it's a right prism so we can use our equation, whose bases are regular pentagons. So what does that mean? That means this is a pentagon. This is a pentagon. And it's a regular pentagon, and so all of these lengths are the same. I don't know if it looks the same in the picture, but they tell us the lengths are the same. So that is the same as that is the same as that. They're all the same, okay? And this is the information that it gives you. It tells you that the length of one of those sides of the pentagon is 8 meters, and the height is 15 meters. So that's pretty huge. It's not exactly a soup can. Maybe it's like a building or something that, well, it would be a smallish building, but still 8 meters and 15 meters tall. That's pretty big. So it's kind of like, you don't have to do this in your homework, but I want you to realize what you're doing is kind of like taking a label all around the side and stretching it out. And this is how it's stretched out now. And so if we stretch it out, then this would be 8 meters from there to there, right? But these would also be 8 meters because it's a regular pentagon and it's the same. And what would the height be? Well, the height is just 15 meters. Okay, so if we're calculating base times the height, it would be 15 times 8 plus 8 plus 8. How many? There would be 5, right? Because it's a pentagon. 1, 2, 3, 4, 5. You could simplify that to 15 times 8 times 5, right? And that's how you do it. Or you just, if you want to use the equation for lateral surface area is the perimeter of the base times the height. So they want to know this, so it's easy. LSA is equal to the perimeter of the base, which is 40 meters, because it's 8 plus 8 plus 8 plus 8, times the height which they told us is 15 meters. And then if you do the math on that, you get 600 meters squared. Why is it squared? Because this is an area. And so make sure you get your units right. It's an area, so it's meters squared, because meters times meters gives you meters squared. All right, that's it. That's actually it for today's lesson. Not too bad, right? So hopefully you understand it all. It makes sense to you. You are going to be a rock star at today's homework assignment. So good luck doing it. Have fun. Bye.